Well, good morning, people. Hope you guys are hanging in there. I assume you saw that I changed the due date on the homework and the quizzes. The due dates aren't that important. It's really getting the stuff done that's important. Okay. And here's where I start to lose circuit students. So it's really important that we started off at 31. We're now at 28. I don't want to lose a single one of you guys here. Okay. So if you're getting to the point where you're going like, I'm going to drop this class, please talk to me. Let's work something out so that you continue in the class and get you to the end. Okay, here we go. Batter up. We need to be where we're at, and here we are, chapter 7. Okay, so when I'm thinking about this chapter here, there's a couple of things that we want to look at. What we're going to do here is that what you're going to see is that there's really a couple of things that you want to talk about. So when I talk about the order of the circuit, that has a very specific meaning. It tells about the number of irreducible, oh gosh, irreducible is one of these big words for me when I start writing in capital words, storage elements. That means if I have two capacitors in series or in parallel, or two inductors in series and parallel, that's still considered one storage element because I can reduce it down to one. So if I talk about a first order circuit, there's only two things that I could say here. It's either an RC or an RL. If I talk about a second order circuit, then there's three things that I could talk about. I can talk about an RLC, or I could talk about an RCC, or an RLL, etc. So that's what we mean by that, the order of the circuit. You're going to see that in this chapter here, we will encounter two different types of sources. And it really tells us exactly how we're actually going to use our techniques to actually solve for these things. So one, we're going to deal with constant sources. And the other thing that we're going to find here is we're going to deal with time-dependent sources. And what you're going to find here is that with constant sources, you're going to find that this is going to be less hard. With time-dependent sources, well, it's going to be hard. Okay, not less harder, but less hard. So this really separates the techniques here. And what you're going to find here is that when we do this here, what we're going to do here is that we're really going to be dealing with what are known as a Thevenin RC circuit or a Norton RL circuit. It really changes how we do this. And then when we get to here, we must derive every first order equation. So what I'm really saying here is that there's a really big jump between these two techniques. And so your job here is to really understand that when we hit these time-dependent sources, you gotta, it's gonna appear that I'm coming out swinging at you. it's not that way. What it really means here is that it's just more challenging. Okay, so the way we typically write this, so then I'm going to start with the first one. If I have a constant source, here's what we say. So for a constant source, we say we're going to look at the response of a first order circuit, and here it is, to a constant input. And the constant input is what? Is a constant source. And so what you're going to see here is that I'm going to tackle the RC circuit first, and then I'm going to go immediately to the RL circuit. And so what I'm going to start with is I'm going to start with an RC circuit. So what do I know? So here's what we're going to do here. So regardless of the geometry of a circuit, of an RC circuit, we will always convert it into a Thevenin RC circuit. Okay, regardless. And the question is, why do we do that? So why do this? And my answer is that I think that this approach is very physical. And what I mean by that is that you can really use intuition to learn about it, right? So this approach is very physical and forces one to really understand what happens in the circuit. Whereas as soon as we get to the time-dependent sources here, we're gonna approach this mathematically. Many books actually start off with it quite mathematical, and they never build the intuition. And that's a real shame, because you don't want that. I want you to understand what it is you're doing, because once we hit the mathematics, it's going to be hard to get you to think in any other way. But if I base you in intuition first, you'll see that it will pay huge dividends later on. So that's why I use the method that I use. I want a physical understanding, not a mathematical understanding. So here we go. Let's do that. So what we're going to do here is that we need to, so we start with an RC circuit. And the geometry doesn't matter. So it doesn't matter what the circuit looks like. So let's say that I start with the circuit like this. Then I have my capacitor. So I got R1, R2, R3. I have a capacitor. And then here, what I'm going to attach here is a switch. So all I know is that this switch is going to close at t equal to 0. What am I interested in? What I'm interested in is calculating the voltage of this capacitor. So when I calculate the voltage of this capacitor, what do I see here? My whole goal here is that I want to convert this circuit. And what do I want to convert it? I remove the cap, and then I find the Thevenin equivalent so that in the end, what I'm really getting, and remember, I'm not going to write VTH. I'd rather write VOC because that's what we really calculate. We're going to get a circuit that always looks like this here. So if I have a circuit like this, then I know how to calculate the voltage of the capacitor. And what you're going to see here is that as I look at the circuit here, there's a couple of things that really come into mind here. So when we look at the process of what actually happens, you're going to see that we're most interested in the behavior of VC of t between 0 less than t less than 5 tau for 0 plus. That's what we're interested in. The problem is we need to find out details about the circuit. So we need details about really VC of 0 minus and VC at infinity. Because what we do then is that when I go and I look at what happens when the switch is thrown, I know where the capacitor starts, and then I know where the capacitor ends. So it's really how this thing is either charging up or discharging that becomes important here. And so what I'm really saying here is that you're going to get something like this here. So our goal here is the complete response. And what I mean by the complete response is that somehow I know what VC is of t less than 0, and that's what we find at 0 minus. Then what we're going to get here is that we're going to get a transient state between 0, t, and 5 tau. So this is, of course, the initial steady state. This guy here is where we're looking at the time behavior of the state, the transient state. And then it finally gets to, infinity. And you're going to see that this infinity is going to be the Thevenin voltage of the open circuit value here. And this will be the final steady state. So this guy here is then what we call VC. Let me write this up closer here. This is VC of t, and this guy is what we call the complete response. In other words, this is how the capacitor responds to a constant voltage source. And so what you're going to find here in this scenario here is that if I was to just kind of jump the gun and, look at the overall behavior, what we're going to do here is that the solution to the capacitor's voltage is going to look something like this. We're going to get something that reads VC of t, and then I'm going to get something that's going to be VOC. Then I'm going to get a second term that reads VC of 0 minus VOC. And I'm going to get an exponential that reads minus t of R Thevenin times C. And so when I look at the solution, what do I know? This is called what? The complete response. Okay. This guy right here has a different name. This is what they call the forced response. That means the circuit is forced to that value. And then finally, they call this the natural response. And the natural response essentially says how you go from the initial state to the final state of the circuit here. So ultimately, what you're going to find here is that it's a complicated process. And these circuits take a lot longer to actually solve. They're way more detailed here. And what you're going to end up doing here is that to get the complete response, you're going to have 4 circuits that you're going to have to solve for. So a typical RC circuit requires 4 different circuits to get the complete response. And what I mean by that is, check this out. So here's circuit number 1.
Back up for a half sec.
So circuit number 1 here is for t less than 0. In other words, for t equal to 0 minus. So this is, of course, this is before the switch has thrown, and that immediately leads to VC of 0 minus. So now you've nailed 1 circuit. Now, when I look at this here, what you're going to see here is that you have circuits number 2 and 3 here. So in this circuit, we're talking about the time equal to 0 plus. And what you're looking at here is that what you're doing here is that now you're converting the circuit into a Thevenin equivalent. So if you don't have, most of the circuits that you're going to see will not have time dependent, won't have dependent sources. But what you're going to find here is that this requires 2 circuits, right? So the circuit means that one of them has to be your VOC circuit, and the other one has to be your RTH circuit. And then what you do here is that you then go in and you do what? You really have a 3rd circuit, but I typically don't call that a 3rd circuit. You know, I could say that now you have your Thevenin equivalent. So that's what I mean by you having this behavior right here. And then you're going to see that what comes out of this thing here is that you'll be able to pick off you'll see that this guy here is, of course, VC of infinity. You have VC of 0 minus. Now you have VC of infinity. And then you have to do one last thing. You now have to solve the circuit problem. And that what that really implies here is that you have to unfold the circuit, right? I have to unfold the circuit and focus on what you have to determine. So there's a lot here. Okay, so to solve one circuit, you got to create 4 different circuits. Really 5, but I don't count the Thevenin equivalent one as a circuit. So there's a lot that goes on. So what I want to do here is that I want to go in and I want to set, and I want to give you an example. And the example that I want to do here is that I want to use this circuit right in here. Okay, so ultimately, this is the circuit that I'm after. Remember, the geometry doesn't matter because we can always get into a circuit here. So now what I want to do here is that I want to go in and I want to convert this into here. So the first thing I'm going to do here is that I want to, so the first thing is, no, let's not say first thing. That's ridiculous. So I want to go through the process of determining the complete response. So the process of determining the complete response, well, you could see what I have it right here, right? Circuit 1 and 2, and then circuit 4. But we're not going to do circuit 4. So here I go. So what I'm going to do here is that I'm going to start off with this circuit right here. Okay. So here I go. So I'm going to start with this circuit. So here I go. So the first thing that I need to do here is that I need to look at what? I need to look at before switch, okay, is thrown. Okay. In other words, at t equal to 0 minus. So when I look at t equal to 0 minus, remember, t equal to 0 minus really equals what? Minus infinity t 0. That means I always have some initial steady state. So what does my circuit look like? Well, the resistor R1 is in the circuit. So when you look at my circuit, it looks like this. And the capacitor is now in open. So in other words, this tells me what VC of 0 minus is. Of course, this is resistor 1, resistor 2, resistor 3. We could see that VC of 0 minus is the same as the voltage across R3. So then this tells me here is that from VDR, I could see here that VC, that the voltage across R3 is the same as the voltage of the capacitor. So then it should be, using voltage divider rule, I get this guy right here. And I get that. So now I know what my VOC is, VC of 0 minus. That's what I have to do for the first circuit. Now what happens here, and this is the important part, this is after the switch is thrown. And what I'm really saying here is that that means here is that the first thing that I got to do here is that I have to convert the RC circuit into a Thevenin equivalent. So let's go do that. Well, once the switch has been thrown, note that that kills off the resistor R1. So if that's the R1 circuit here, what I'm seeing here is that then my circuit looks like this here. So I have my voltage source. I have my resistor. And this is the cap right here. So of course I have R2, R3, C, and now I'm looking for this guy right here. So what do? I remove the capacitor. So what do? We remove cap. And so then what do I get here? I get a different circuit. I get my V source. And again, this is R2, R3, and this guy here is now VOC because there's my A and there's my B. And you could see that I could use voltage divider rule to get this. So immediately I could say here that according to voltage divider rule, it's got to be R2, R3, R3 times V source. I now know what my VOC is. And then the other one is that I then go along this direction here. And what am I doing here? Right? You remove cap and short out VS. So in other words, I now have a circuit that looks like this. And this is R2, R3, and then I look at the opening. And what am I doing here? I'm going to come in here and I'm going to say, I want this Thevenin resistance. And when you look at this Thevenin resistance, what you're seeing here is that you could see that as it goes, R2 and R3 are in parallel. So I could come in here and I can write that these guys are in parallel. So now I have my Thevenin parameters right here. So those are my two circuits, and what I end up happening now is that, so now we have a Thevenin equivalent. And when you do that, what you find here is that I get a circuit that looks like this. Here's VOC, I have RTH, and now I can put my capacitor back into the circuit. And I have my cap. So now this is VC of T. Okay, so then the next step here is that now that I got it into an RC circuit here, I want to go and I have to calculate the details of this thing here. So now what I want to do here is that I want to solve for VC to determine the first order equation for the cap here. So here's what I'm going to do now. So when I'm looking at this thing here, what we know is that this is a series circuit. And because this is a series circuit, the only thing that I can do here is that I have to talk about voltages. So because this is a series circuit, we must use KVL. There's no voltage divider rule anymore. Okay, there's no voltage divider rule anymore. So I'm going to use KVL, and what I'm going to do here is that I'm going to go around the loop here, and if I sort of stick in my polarities, this is kind of I would expect for our Thevenin. So if I do this, we can see here is that it's got to be like this here. So this tells us that we do what? That VOC, the source voltage, has to be the combination of RTH plus VC. And then what I'm going to do here is that I know that the voltage across the Thevenin resistance must be related to what? The current of the capacitor, because it's the capacitor that's dominating this thing. But wait a minute, the current of the capacitor, which is the capacitor equation, reads like this. So if I substitute this into here, what you're seeing then is that I'm going to get a RC constant, dV dt, plus Vc of t, and this guy is my source. So right away, what you're seeing here is that this is my first order equation. But this is not the customary way to write this. I could write it this way and it would be totally legit here. But what we want to do here is that we want to rewrite this equation for later usefulness, if I could say this. Because we're going to get to the RL circuit and it's going to behave in a very analogous way. So what I'm going to do here is I'm going to isolate dV dt, which is a very common thing in math and physics. Excuse me, physics and engineering. So if I isolate here, so what I'm going to do here is I'm going to isolate dV dt, and when you do that, that means I got to divide everything by the RC constant. And so now, this is the form that we want. And this is what I really call the first order equation, right? So this is our first order equation. And that's what we got to solve. So now that I got that, like I said, I want to make it useful for later on. And so what I'll do here is that I'll start solving this thing. So what I want to do here is that I want to make a change in variables so that it's easier to translate. So what we're going to do here is that we're going to change variables for easier use later. So what I'm going to do here is that I know that I have my first order equation. I'm going to let x equal to Vc. And as you could possibly imagine, since I have this RC constant, they typically define the RC constant with the symbol tau. So it's not really RC, it's R Thevenin. That's the appropriate way to think. And because I have a constant source, the right-hand side, I'll label as K. I could label it anything I want. You could see here that that's going to be VOC divided by RTH. So I have these three constants. So what I'm going to do here is that if I substitute this into this equation here, you're going to see that now my first order equation really looks like this. dx dt plus x over tau is going to be equal to k. So you can see that k and tau are related, but this guy is a very generic form here. And this generic form is what we really want to look at. So what I'm going to do here is that I want to solve for x here. By integration, right? This is an integral equation. So what am I going to do? I have to isolate x. Okay, so the way I'm going to isolate x here is that I'm going to rewrite, and I'm going to bring my x over tau term to the right. So then I'm going to go dx d tau, and then I'm going to get a common denominator. So I'm going to get a minus, and this is going to be x minus k tau divided by tau. So note that that is exactly the same. So from here, what we want to do here is that we want to integrate this. So if I integrate this thing, look what I got to do. I got to isolate the x terms, and I got to isolate the time terms. So if I do this, I can write this like this here. And then my time term is on the other side, which will be dt over tau. So again, tau is a constant. So then if I integrate this thing, what I'm going to get here is that I'm going to get the following thing. Clearly, I get this as the natural log of x minus x tau. And on the other side, I'm going to get minus t over tau right here. But this is an indefinite integral. Because this is an indefinite integral here, I have an integration constant. And this integration constant is an arbitrary constant. But I need to isolate x. So what am I going to do? I'm going to take the exponential of both sides. So if I take the exponential of both sides, what you're going to see here is that then I get this guy here. Then it reverses this. So this goes x minus k tau. I'm going to define this as I'm going to get e to a constant times e to the minus t over tau. And since e to a constant is a constant, I'm then going to come in and write down an arbitrary constant, which I label t. So then I isolate x, right? So then if I isolate x, you see that my solution then looks like this. You're going to have a constant that's going to be k tau plus a e to the minus t over tau. And this is my solution. This is my first order solution with arbitrary constant. And in this case, the arbitrary constant is a, because that's related to the integration constant here. So as always, when you have a differential equation, you have to apply the initial conditions here. Okay, so we know what k is. What is k? It's VOC, which we already calculated. And then we already calculated RTH and C. So those are constants that we already know. So what we really want to do here is that we want to apply. So now what we're going to do here is that we need to apply the initial condition to determine the constant A. So here we go. How do we do that? We apply the initial condition, as of course is what we know here. And so what we do here is, remember, we know what k is, we know what tau is, we don't know what a is. So then what we do here is that we come in and we go, okay, so at 0 minus, we know that that's our initial condition, right? So x at 0 minus is our initial condition. So this implies here that if I now apply this to our first order solution here, you could see here that this is going to be k tau plus a e to the 0, which then tells me that this guy has to be k tau plus a. In other words, I know what a is. So then this tells me here is that a then is then going to be x of 0 minus k tau. So now I have defined my initial condition here, right? We measured x of 0 minus, or we calculated in the circuit, but typically we measure it in the circuit. And of course, we know what k is because we have VOC, and we know what tau is because we know the Thevenin voltage, the Thevenin resistance, and the capacitance. So we know these. So we have we have this down here. But what I'm going to do here is that just to make it a little bit more clear, because it's going to be, we want to get it to the right form, I'm going to bring in another thing here. I'm going to look at the infinity, right? And this guy is the final steady state. And if I do that, there's some really beautiful things that we can see here, because now what it tells us here is that x at infinity for our solution then looks k tau plus a e to the minus infinity. And of course, anything to minus infinity is 0. So then that tells us that this guy is equal to x infinity. So when I look at this, I now have this here. So now what I'm going to go do here is that I'm going to go rewrite our equations here. So it turns out that there's another way that you can look at this thing here, is that as soon as I do this, look what happens to A. We can now rewrite A, because A, which is x of 0 minus k tau, look what happens. This is x of 0 minus x at infinity. That makes it extremely useful for us. So now I've defined my constant A, because I now know what x tau is in terms of x infinity. So here I go. So now what I'm going to do here is that I'm going to rewrite now the first order solution with initial condition applied. So if we do that, I have x of t, and this is going to be k tau plus a e to the minus t over tau. But note, we know what x t of tau is. We already said that that's x infinity. And then a, we saw here that it looks like this, times e to the minus t over tau. This is a very important result, because this guy tells us about the force response. This is what the source is forcing the capacitor to do. And this here is the natural response. And what the natural response tells us is that how the capacitor decays from its initial state to the final state. So now, here we go. If I now translate this guy into the capacitor relationship, so now applying to the Thevenin RC circuit, we see then if I have an equation that looks like this, there's a solution. The solution is going to look like this. It's going to say that VC of t is going to be equal to VOC plus the initial condition of the capacitor minus VOC times e to the minus t over tau, where tau is RTHC. This is what we were after. And our job is to master this equation. Okay? I want to master this equation. You got to know this deep in your bones. Okay? You got to be a master of this equation, because this is going to guide you very strongly when we get to the intense mathematics. Okay? I'm going to rely on this thing so much. Even when we get time-dependent sources, I'm still going to rely on this equation. And when we get to RLC, even though solutions look differently, I'm still wanting you to understand this because this will help you in understanding even RLC circuits. So my job here is that now I want to go do physical interpretation of the solution.
Hey, Carlos, I have a question.
As many as you want.
I think earlier you had written K equals VOC over R Thevenin, and I wasn't sure what happens to the C term on the right side. I think a little earlier than this even.
Are you talking the A term that I called?
I think one more line up on the page, you see that VOC over R Thevenin C
Oh,
on the
God.
right-hand side.
God damn it, Sean. Stop making me look bad. You're right. I did forget that C. Very nice catch. Thanks for the help. I appreciate that.
No problem.
Yeah, keep me honest like that. I like it. Okay, let's interpret this thing now. So, does this solution make sense? Does this mathematical solution satisfy the initial conditions? They better, right? So if I look at my circuit here and I set t equal to 0, what am I going to get here? Well, I should have, my solution says it should be VOC plus VC of 0 minus VOC, but then I get e to the 0, which then tells us that that's 1, of course, and you could see that this guy cancels out with that guy, so that in the end, I get VC of 0 minus, which is exactly what we want. Now, remember, of course, VOC of 0 minus is the same as 0 VOC plus. So that looks good. The other thing that we should see here is that VC of t equal to infinity, I'm going to get what? VOC plus this whole quantity, then I'm going to get e to the negative infinity. And of course, anything to negative infinity like this is going to give me 0. So then again, I get my final steady state of VOC. So far, so good. Now, let's hit something fairly substantial. Let's look at what the solution tells us. The second thing that we want to look at is we want to look at a charging, discharging capacitor. So you got to nail this piece here, okay? Because what we're going to do here is we want to look at what the mathematical language is, whether I have a charging capacitor or whether I have a discharging capacitor. So here we go. So we're going to start with a charging capacitor. So what does it mean to be a charging capacitor? So let's look at this thing. So a charging cap increases in voltage from VC of 0 minus to VOC. So what does the solution look like? So in other words, VC of 0 minus must be less than VOC. Of course. So what this tells me here is that, look at the solution now. VC of, by the way, I need to define something. I'm going to define the delta V, okay? And I'm going to define this as the absolute value of VC of 0 minus VOC. Okay, so this is a definition that I'm going to use. Okay, so now let's go look at the solution. So when I look at this solution here, what we're going to see here is that what you're finding here is that VC, so this implies here that when I look at a charging capacitor, what does this mean right here? Well, I see that, so I'm going to actually scan down a little bit. So now the cap's voltage looks like what? Well, I got VC of T, I got VOC, and then at this point, I've been calling this VC of 0 minus VOC times e to the minus t over tau. But now look what I'm going to do here. I want to look at the absolute value of this guy right here. If it's charging up, we see that this quantity is negative. So this guy really reads VOC minus. So if I see a minus right here, that minus sign tells us that I have a charging capacitor. So our solution says that if I get a negative number right there, I have a charging capacitor. Okay, I have a charging capacitor. So picture-wise, what does this look like? Well, it looks like this. There's a picture that I'm going to draw here is that you could imagine that I'm coming in with what? I'm coming in at some initial voltage. And then I'm going to charge up to a voltage here. And this line represents VOC. So what's going to happen? As soon as the switch gets thrown, this guy then charges up to that right there. So let's be real careful here. You can see here that when I look at this thing, the height change has to be this delta V. So this thing from here to here is my delta V right there. That's the difference between the initial and the final voltage here. And all this thing is really saying here is that there is work being done by the battery's potential to increase the voltage of the capacitor. So if I was thinking about this in a physical way, you could imagine here that I have my lower plate of the source, and then I have my positive plate up here of the source. And what I'm seeing here is that the height change from here to here is VOC. So now what happens here? Well, I have a capacitor. Here's my capacitor right here. And the capacitor is starting off from a height of what? VC of 0 minus. And so now what's it going to do? It's going to then, oh, damn, I made a mistake here. I have an error. My bad. It's not VOC, it's V of the source. Here, I gotta calm down my damn dog. Toto, hush up. Okay, so now look at the incline. I have an incline from the source. My incline from the source goes like this. And then what is the capacitor doing? It goes to a higher energy state. Okay, goes to a higher energy state up the incline. So now, what is the height of the capacitor? Well, from here to here, the height of the capacitor now is VOC. So you're charging the capacitor to a higher voltage. So it's moving up the incline. That's what that picture means right there. That's what this equation means. Okay, so let's go to a discharging capacitor. So a discharging capacitor, you could imagine, is going to have just the opposite. So now I have a discharging So in this scenario here, what does the mathematics tells us? Well, if I have a discharging capacitor, right, just like I said before, right, if I have a discharging, instead of an increase in voltage, there has to be a decrease. So a discharging cap decreases in voltage. So if I now look at the term VC of 0 minus VOC, you could see that this has to be positive, since VC of 0 minus is greater than VOC. So if that's the case here, look at what the solution here. So mathematically, you're seeing here is that the voltage of my cap now is going to be VOC, which is then going to be plus VC like this. So now if I put it into the language that I've been using, check it out. This should be VOC, but this time, instead of a minus, I'm going to get a plus sign right there. So therefore, I get this type of thing happening. Okay, if I get this type of thing happening, we know that this quantity right here is positive, whereas before it was negative. So then that tells me, the plus sign tells me, right? So the plus sign indicates discharging. So then I play the same game as I did before. So if I go and I look at my curves, what are my curves looking like? Well, they got to be looking something like this here. So let's say that I'm plotting, again, VC of t, and then this is t. So what am I seeing here? I'm seeing this time that I have an initial VC of 0, and we know that that's higher than VOC. So that means here's my line right here. And then it discharges to a lower rate. So that means this guy is going to be my VOC value. And so as it discharges, what am I going to see? Well, I'm going to see that this guy goes like this. It discharges to the lower rate here. But the question is, what about this delta V? The plus sign indicates that you have dropped from here to there. So that plus sign tells us there's a drop in the voltage. And then again, the same picture that we drew before. What does this mean physically for the source and the cap? Well, what you're seeing here is that you can see that this guy again is my source voltage. And now when I look at my capacitor, it started off here. And this height, of course, is my VC of 0 minus. And then the capacitor then falls down my incline to this height right here, which is then VOC. So it's discharging. And in the RC circuit, what that really means here is that, how do I say that? In this circuit up here, what this really means here is that there's still current flowing from V source to V cap. This is the opposite case here. Here, the capacitor in the RC circuit is discharging. So that really means that in essence, VC of T is discharging into the source for a brief moment of time. So I'm getting current flow in the opposite direction. That's what the plus sign actually means here. Okay, so let's go to the third thing. The third thing that I want to analyze here, which is super, super important, is the time constant, which is defined as RTHC, which is, of course, tau. The behavior of the circuit completely depends on the component values. Now, I have been writing this circuit information in terms of the most common way to interpret it. I actually don't like the way this solution is written. But if you go online, this is the way you see the solution. This is not my preferred way to see this here. So to get a sense of what the time constant really does, so to understand the role of the time constant, it's best to rewrite the solution. And when you go to higher level differential equations, you find that the way I've written it to there, that's not the standard way. And when I get to the second order differential equations, this is exactly the way I'm going to write it. And so here's what I mean by rewriting this. So the way you want to rewrite this here is it goes like this. And you know what? I should step back and say one more thing. Why don't I rewrite it like this right from the beginning? It turns out that mathematically, it's better to write it the way you're seeing it right now. Because when you solve a differential equation, this is the way your solution is going to look like. Whether you use Math 7 techniques or whether you use my technique, it doesn't matter. You get that. However, it's not the most apparent thing for intuitive understanding. This is the way you want to write this, but you'll never get a solution of this form. And it looks like this. So let's look at the way it started off as. And what I want to do here is that you now want to collect like terms. And if you collect like terms here, what you're really seeing here is that I got my initial value that looks like this. And then I got my final value that looks like this. And one of the things that I really write a lot here, especially in Physics 4B, when I'm explaining RC behavior, is that I call this V initial e to the minus t over tau plus V final of 1 minus e to the t over tau. This is my absolutely favorite way to do that. And what you're seeing here is that you're seeing two behaviors. This guy tells us how it discharges from the initial value. This guy tells us, if I'm talking about a charging capacitor, that this is how it charges up to its final state. And the best way is the table that I created here, which looks like this. So let's go look at this table here. And what this table does here is that it's really a statement of KVL. And what you're seeing here is that if you start to look at this in terms of a bar diagram, which I think is really nice to look at when you're looking at this thing. It goes something like this here. So let's plot this thing. So the only thing that we know of right now is that the full voltage, that the maximum voltage that the system can have is going to be the source voltage. For a DC circuit, KVL holds, man, that thing, it grips the voltages and it forces them to be the values that they are. So look what happens at 1 tau. So for example here, let's say that this guy is equal to 10 volts. So 10 volts here is the constant source value. And I can't change that. That's what it's fixed here. So then what does KVL tells us here? Well, if I have an RC circuit, right? You know what? I said VOC. And I wrote, I mean VOC here. So I'm looking at VOC, the resistor, and then I have the cap here. So when you look at this thing, at one time constant, what do I see? Well, if this thing is 10 volts, you could see that at one time constant, it's going to be what? Well, the voltage across the resistor is going to be about 3.7 volts. Okay, you could see that this guy is going to be the voltage across the Thevenin resistance. After one time constant, right? After one time constant, this guy charges up from 0, right? If I look at this, this thing is going to go all the way up to here. And this guy's going to be the voltage of the cap. So right away, you're seeing that this thing, after one time constant, that it charges up to 63% of the value. That's what we mean by exponential charging. And then you go to 2 tau. And if you go to 2 tau, what you're seeing here is that if the voltage of the capacitor is increasing, then the voltage of the resistor must decreasing because it's getting more and more open as time goes on. So you're seeing the drop of the resistor to look like what? Well, it's now at 1%. So I don't know what 1% looks like, but let's say it's this amount right here. It's this little tiny amount. So, that's not 1% here. You could see that it should be 14%. Ooh, that's a mistake. That's a typo. This guy should say 14%. So it drops to about, I don't want to say half the value, it's a little bit less than half the value. So it drops to about right here. So if it drops to about right here, what you're seeing here is that, again, this is VR, and this is really going to be about, 1 point. Am I getting this right? Yeah, it has to be. It has to be that. It's got to be 1.4. So it's 1.4 volts, and then the cap voltage you could see is totally starting to dominate. And you're seeing how this guy is getting, bigger and bigger. And then after 5 tau, which is when we call the steady state, you could see that the green here is just this little tiny line here. The lion's share of this whole thing is with the cap now. So what I'm seeing here is that you're really seeing how this guy is charging up. It's just dominating this guy. So after 5 tau, we say the cap is fully charged. It's not, right? It's not really fully charged, but that's where we cut the thing off here. I mean, think about the atmosphere. The atmosphere goes way up beyond what we call the end of the atmosphere. The definition of the end of the atmosphere is when it reaches 1/100th of the atmosphere at sea level. So we call the end of the atmosphere at 40 kilometers. So the question is there atmosphere above that? Absolutely. But it's so minuscule that we just don't think about that. The same thing happens with the charge of the capacitor. At 5 tau, the vast majority of the charging has been done. So 99.3 is what we say is a fully charged capacitor. So what I want to do now is that picture-wise, what does this RC constant mean? So what we're seeing is we're seeing something like this here. So then if I look at this, what does it graphically look like? Okay, so what we've seen here is that we can see here is that if I'm looking at a charging capacitor, so this is V of a cap that's charging, what you're seeing here is that according to these values, exponential decay, you're seeing a curve that actually looks like this here. And the value that it's going to reach is always going to be this VC value. And we've already kind of talked about this before here. And when you're looking at this curve here, right in here, we get a very quick increase. And you could see, right, we went from 0 to 63% charging in one time constant. But then as I get from here to here, you get a slow increase. A very, very, very slow increase. And in a very analogous way here, you're going to see here that the discharging behaves exactly the same way. So then if I come in here and I look at the discharging, V cap discharge, you're going to see the exact same thing. If I have a discharging cap, which you should expect here, that we're approaching VC here, and when you're looking at this guy here, what you're finding here is that, again, right in here, we have a very rapid decrease. And then as I go from here to here, this is a very slow decrease. And that's because of what the time constant is telling us here. And the thing that determines, so the one thing that determines the rate of charging up / discharging is the time constant, which is, of course, RTHC. So it only depends on the Thevenin resistance, and it only depends on the capacitance. That being said, I want to go through the problem-solving process so that we could start looking at the first example here. So here's what we want to do here. I want to take 2 examples, and I want to go through this problem-solving process. And so the first thing that we want to look at here is that we want to look at, I see this as a 4-step process. So remember, this is so important. Constant sources. You try to do this to dependent sources, dude, I'm just going to give you 0. Maybe I might give you 3 points. This is only true for constant sources. And we're doing it this way because we want to learn physically what is happening in an RC circuit or an RL circuit. Once we get to the mathematics, all hell breaks loose. So here we go. It's a 4-step process. So what do? I determine the cap's initial velocity, VOC. So again, there's very particular things that we're going to be looking for. We got to go get VOC. That's the first thing. And then what am I going to do? We're going to throw the switch, and then we're going to convert it into Thevenin parameters. That means I got to get 2 parameters from that Thevenin circuit. I'm going to get VOC. I got to get RTH. Once you have RTH, I call the time constant a Thevenin parameter because it depends on R Thevenin. So I need 3 parameters from the second step here. And note, I'm not looking for the time constant. I'm looking for 1 over the time constant. And then finally, what am I going to do? I'm going to put it into solution form. Once I have the solution form, then I'm going to go back into the circuit and I'm going to solve for the appropriate parameter. So let's go do this here. So I want to apply this process to this example. So here we go. Let's go nail this thing here. Okay, let's go nail this thing. So you could see that the switch closes at t equal to 0. And what I want to do here is that I want to solve for VC of t. And you could see that it's for t greater than 0, but it really means that I'm talking from minus infinity to positive infinity. Okay? So here we go. So the circuit's always in steady state. We always assume steady state before the switch is thrown. And what I want to do here is I essentially want to see if I can physically understand what is happening first. Okay, so my first step here that I'm asking you to do here is that I want to determine VC of 0 minus. And typically what I try to do here is I try to look at this thing physically. So note, you can see that as soon as the cap goes to an open, it's going to kill off everything and it's got to be at 3 volts. And then as soon as the switch gets thrown and I go to a steady state, it's going to kill off the 6 ohm resistor. So let's go do this. So the first thing that I'm going to do here is that I'm looking at t equal to 0 minus. This tells me then that the circuit goes like this. The cap is what? The cap is now at steady state. Since there's no current in the circuit, VOC is 3 volts. So now I got that. Okay, now I got that. So the next thing that I want to do here is that now the switch is thrown. So here I go. So now what I want to do here is that I want to determine the Thevenin parameters. And that implies I want VOC, RTH, and I want 1 over the time constant. So let's go do that. So what I'm going to do here is that now, here's my circuit here. So at t equal to 0 plus, I have a circuit that looks like this. This is my circuit. So what I'm going to do, I'm going to remove the load, right? And if I remove the load, then I have this circuit right here. And I know this is a 6, 6, 3, and I need 2 things. I need VOC and I need RTH. I need those 2 things. So here I go. I'm going to do now is that I'm going to go determine VOC. So this circuit then says this. I have 3 volts. I know this is 3. I know this is 6. This is 6. And I'm after what? VOC. So I can see here is that VOC is the same as So note that this 6 ohm resistor is dead. So then this VOC has to be the voltage across the 6 ohm. So therefore, using VDR, right? If I use VDR, you can see here is that I can, right? I'm going to use VDR tells me that this has to be 6 plus 3 times 3 volts. So therefore, I'm going to get 2 volts. And this is going to be my VOC. So I got one of them. Oh, damn, I'm out of time. So I'm going to have to stop here. Okay. I'll see you Friday, people, on Friday. Otherwise, I'll see you guys on Monday, man. Take care. I'll talk to you guys later.